In this tutorial, we're going to calculate the NMR spectrum of a molecule. In this case, we're going to use ethanol, which we have here already on the screen, and we're going to do the proton spectrum of ethanol. The first thing we have to do is select all the atoms that we're going to use. In this case, we're doing proton spectrum, and we're going to put a nuclear spin at the nucleus of each of the protons, of which there are 6 here, so we have to select these 6, and we'll do so in this fashion. Oops, got to get rid of that one. So we have 6 protons selected, and we go up and we name these as the NMR atoms. This will put a spin at the position of the nucleus of these atoms for the NMR program. Next, we bring up the NMR module like this. Here's the NMR module. We've transferred our molecule over to the NMR module, and we have to do the setup appropriately. Now, the setup has the possibility of using mixed molecular mechanics, quantum mechanical calculations, and having a subset, which are quantum atoms. And we're not going to do that. Everything is quantum atoms. So then there's the question, which are the NMR atoms which have the spin on it? And we've already set those, so those are fine. There's the next question is equivalent atoms, and this is something we want to set because the 3 methyl protons rotate in the NMR time frame, and they are basically equivalent protons, and we have to set them so. And so we're going to have 2 sets of equivalent atoms. The 3 protons 7, 8, and 9 are the first set, and that's the first set. The second set is 4 and 6, and so we apply that, and so we have 2 sets of equivalent atoms, 1 and 2. We are not using deuterium nor carbon-13 or something. We have the normal isotope, so we don't need to label any atoms. And we're going to do shielding and chemical shift, spin-spin coupling rather. We're going to use TNDO2, which is a version of INDO, and so we're basically ready to go. The calculations can be done in 2 phases. The first phase is an electronic structure problem that calculates the shielding and the coupling constants as an ordinary problem in electronic structure with molecular wave functions, and we have to do that to get the shielding and the coupling. Given shielding and coupling that we've computed, or shielding and coupling that can come from experiment or anywhere else, there's a second phase of calculating the NMR spectrum that uses the NMR Hamiltonian as a completely separate kind of quantum mechanical problem, and we can do that as phase 2 if we've done phase 1, or we can do phase 1 and then phase 2. We'll just do both of them. These are very quick calculations, and now we have a bunch of shielding constants and appropriate chemical shifts. The chemical shifts are based on a reference shielding that we have actually put into the program. The reference shielding for protons is 23 parts per million, and so the chemical shift is calculated relative to that value. And again, these values are averaged so that there's 3 here of the methyl protons, and these are the methylene protons, and this is the proton on the oxygen, which has a much larger chemical shift. The coupling constants are here, and the spectrum is here. Now, if we impose a line width on that, we'll see there's a 3 to 2 to 1 ratio. These are the methyl protons, the methylene, and the hydroxyl proton. We can zoom in on this, zoom back out, and so on, and explore this spectrum. The line width that we apply is just a slider with an arbitrary line width. We don't compute line widths, but we can make all the line widths equal and apply a line width function if we like. Again, that can be a Gaussian or a Lorentzian line width if normally it's Lorentzian. Anyway, that's a computation of the NMR spectrum for ethanol.